This Regents chemistry video is on balancing equations. So the key with balancing equations is we just need to make sure that we have the same number of atoms on the left side that we do on the right side. So the number on the left and the right needs to be equal. And this must be true for every element that's a part of the reaction. So assuming that we have a reaction that has, let's say, hydrogen and oxygen, that means we need to count up all the hydrogen atoms on the left side and make sure that the number of hydrogen atoms on the right side is equal. And the same thing with the oxygen atoms. We'll need to count those up on the reactant side, the left side, and make sure that the product side, the right side, is the same. So really all we're going to do here is count the number of atoms, and it's really that simple. So the steps we want to take are just to check the elements one at a time. So as I was saying, we'll check the hydrogens and the hydrogens. If they're good, then we'll move on and do the oxygens and the oxygens. So it's really important here to only do one at a time. This can get really overwhelming if you kind of look at it as a big picture as opposed to just one element at a time, because that's really what we're checking. And just as a little hint here, in most cases it'll save you a little bit of trouble if you save hydrogen and oxygen for last when you do your balancing. So let's take a look at a couple of examples here and see what I mean. So if we have an equation, copper plus oxygen makes copper oxide. Is this a balanced equation? Well, we could think about it in terms of each element, and this is really the process we want to take. So we have one copper atom on the left side, the reactant side. Again, this arrow separates the two, so we can kind of divide down the middle there. We've got one copper on the left and one copper on the right. So if we have the same number on the left and right, that's good. We're ready to move on. So we can look at the oxygens. We have two oxygen atoms on this side because of this subscript 2 here. We have one oxygen on the right because if there's no subscript, we assume 1. So this is unequal. So what we need to do, the way we balance equations, is using coefficients. So you've probably already seen some examples of equations that have coefficients in them. The purpose of the coefficients is to balance the equation by the law of conservation of mass and by conserving each atom from left to right. So if we have two oxygen atoms here, we want to think, what coefficient could we put here to get two oxygen atoms on the right side as well? So pretty easy here, we can put a 2. And it's very important, these coefficients get distributed. So this 2 now applies to both the copper and the oxygen. The coefficient applies to all parts of the compound that it's in front of. So now we have, instead of 1, we have 2 coppers, and instead of 1, we have 2 oxygens. So the oxygens are now, we've fixed this. With the oxygens, we have 2 and 2, those are equal. But the coppers, we have 2 and 1, those are now unequal. So the way we can fix that, we need to just add another coefficient here. We can put a 2, and now the copper has 2 on the left and 2 on the right. So 2 coppers, 2 coppers, 2 oxygens, 2 oxygens. This equation is now balanced because both of the elements have the same number on the left and the right side. It just so happens that there's 2 oxygens and 2 coppers. These two numbers here do not have to be the same. Oxygen only has to equal oxygen. It does not also have to equal copper. That's just a coincidence in this case. So we can look at this visually, and this is what the balanced equation would look like, because once we balanced it, we said we had a 2 here and a 2 here. So now we have 2 copper atoms, 1, 2, and 1 oxygen molecule that consists of 2 oxygen atoms, and it makes 2 molecules of copper oxide. So that's 2 copper atoms, which matches up with this, and then we have 2 oxygen atoms, which matches up with this. So essentially before, let's wipe this out and see what we would have had before the balanced equation started. We had 1 copper here, so we essentially could take this one out and say we had 1 copper plus 2 oxygens making 1 copper oxide, so we could take this bottom one out. If we look at this here, we have 1 copper atom plus 2 oxygen atoms making 1 copper and 1 oxygen atom. So this second oxygen atom, where did it go? It just magically disappeared based on this unbalanced reaction. So again, based on the law of conservation of mass, we have to conserve mass from the reactants to the product side, and in this case we magically destroyed some mass. So we can't magically destroy mass or create it. It has to be conserved from the reactants to the product side. Alright, so let's take a look at another example here. We've got 2H2 plus O2 making 2H2O. So there's a little bit of clarification here with the coefficients. Again, I said that these get distributed. So what I mean by that is this 2 here, it gets distributed to both parts of this compound. So the hydrogen and the oxygen in this water molecule. So essentially we had 2 hydrogen atoms to start with because of this coefficient. Because of this subscript, excuse me. The subscripts and the coefficients get multiplied. So essentially now we're going to have 4 hydrogen atoms. And we had 1 oxygen to begin with, times 2 because of this coefficient would give us 2 oxygen atoms. So it's really important to make sure that these coefficients get distributed. So on this side we have 2 oxygen atoms, and on this side we have 2 times 2 would give us 4 hydrogen atoms. So then if we look at this equation, we've got 4 hydrogens, so that's good. 2 oxygens, that's good. We have a balanced equation here because both of the elements are the same on the left and the right side. So we could look at this one visually as well and say, okay, we've got 2 hydrogen molecules here, which each consist of 2 hydrogen atoms. So we have a total of 2 plus 2 makes 4 hydrogen atoms here, and here we have 2 and another 2 making 4. And then if we look at the oxygens, we've got 2 over here, 1, 2 over here. So total we have 2 oxygens, 4 hydrogens. This now balances out. So I'm hoping that these visual representations are helpful for some of you who are a little more visually oriented, but it's really just a matter of counting the number on both sides. So let's take a look at another example here. We've got CH4, methane, plus oxygen, making carbon dioxide and water. Is this a balanced equation? So this one we have a couple more elements involved. What we want to do is the same exact process that we were doing before. So we'll save the hydrogens and oxygens for last here. So we're going to start with the carbons. So on the left side we have 1 carbon. On the right side we have 1 carbon. So the carbons are balanced, we're ready to move on. We have 4 hydrogens here, and we have 4 hydrogens here. So 4 hydrogens and 4 hydrogens, those are balanced. We can move on to the oxygens. We've got 2 here, and we've got 2 plus another 2, because we have 2 times 1 would give us 2 here. So it's important to remember, now we're going to have 4 oxygens, because the entire product side counts. So we have 2 oxygens, that makes 4. So the total number of atoms on each side is what needs to be balanced. So we have 2 sources of oxygen here, 1 and 2. So both of those need to be taken into account when we do the balancing. So we have 4 oxygens here, 2 here. So you can probably figure out that the coefficient we need to put here is 2, because 2 times 2 would give us 4 now for the oxygens. So 4 oxygens, 4 hydrogens, 1 carbon. We've balanced all of the elements in this equation. So if we look at this from a visual perspective, this is the unbalanced equation that we started with, and then we ended up throwing a 2 in front of this oxygen and getting this balanced equation down here. So visually we see we have the black atom here is carbon, we have 1 and 1. The hydrogen atoms here are a little hard to see in this 3D drawing, but basically there's 4 of those, and then 2 and 4 hydrogens over here. We have 2 plus 2 making 4 oxygens, and then 2 here, another 1 making 4 oxygens as well. So all of these are balanced. So far we've been just verifying equations to see if they're balanced or not. Now we're going to try just balancing them like we've kind of already started to do. So if we start here, we've got 2 nitrogens and 1 nitrogen. So what we need to do with this is throw a coefficient of 2 in front of this NH3 ammonia. So we now have, instead of 2, we have 2 nitrogens, so 2 and 2, that checks out. Hydrogens, we have 2 on the left, and now because we've added this 2 here, this is going to count, and we have 2 times 3 would give us 6 hydrogens. So again, these coefficients and subscripts get multiplied together to give us 6. So we have 6 here, and we need to think what coefficient here times 2 would give us 6, because we need 6. That's the hydrogens we have on the product side. We need 6 on the left as well. So what times 2 would give us 6? That would be 3. So a coefficient of 3 goes there, and then this would be the balanced equation. So a 1 in front of the nitrogen, a 3 in front of the hydrogen, and a 2 in front of the ammonia. So again, it's just the same process of taking one element at a time. So if we've got C2H6 plus O2 making CO2 and H2O, how could we balance this? Well, we'll start with the carbon because again, we save the hydrogens and the oxygens for last. So we've got 2 carbons here, 1 carbon on the right. So in order to correct for that, we'll throw a 2 here, and now we have 2 carbons. So 2 carbons, that's good. We can look at the next element. We've got hydrogen. We've got 6 here, but only 2 here. So what times 2 would give us 6? We could put a 3 here, because now 3 times 2 would give us 6 hydrogens. So now we could count up the oxygens. We have 2 on this side, and then we have 2 times 2 would be 4, 3 times 1 would be 3, so this would make 7 oxygens. 7 oxygens on the right, 2 on the left. So there's 2 ways to do this. One way is to use a fraction. So we could put 7 over 2 in front of this oxygen, because 7 over 2 times 2 would give us 7. So the way we really did that was, if we call this number x, we could say 2, because that's our subscript, 2 times x has to give us 7, because that's how many oxygens we have on the product side. So then if we solve for x here, we get x equals 7 over 2. So that's one way of doing it, is with a fraction. So I'm just going to erase this real quick and put down the coefficients that we had up to the point of balancing the oxygen. So the other way of doing this, we said everything else is balanced so far except the oxygen, so we have 7 oxygens on the right side, and we have 2 oxygens on the left. So the other way of doing this is basically saying what common multiple we have between these two numbers. So we have 7 here and 2 here. So what that means is that we can multiply this by 7 and then this by 2, so 3 times 2 would give us 6. And now we have 6 oxygens plus 4 oxygens would give us 10, and 14 oxygens on the left would give us 14. So basically we threw this out of balance now. So what we could do to correct for that is add a 2 here and a 2 here. This multiple method is a little harder to see in this example, but basically, I meant multiply by 2 here, and this would then give us 4. 2 times 2 would give us 4. So by doing this, we now have 4 carbons. We would have 12 hydrogens and 12 hydrogens, and then we would have 14 oxygens and 8, because 4 times 2 plus 6 times 1 would be 6, so 8 plus 6 would give us 14 oxygens. So honestly, if you can do the fraction method, that's really the way to do it. But if you can't, then you can use the common multiple idea, and then you just kind of have to correct for the other elements that you may have thrown off by doing that. So another example we've got here, iron and oxygen making iron oxide. So we have 1 Fe and 2 Fe's. So to correct for that, we can put a 2 here. So we've got now 2 Fe's and 2 Fe's. That's good. We can move on to the oxygens. So here we have 2 oxygens and 3 oxygens. And this is where the multiple method will be a little more useful, because this is a bit of a simpler equation. So we could, using the fraction method, put a 3 halves here, and then we would have 3 oxygens on the left and 3 on the right, and then that would be balanced. But it could also be done with the multiple method. So we could essentially see that the multiple of 2 and 3 here would be 6. So to get there, we would put a 3 here and a 2 here. So now we have 6 oxygens, 6 oxygens. Now though, we have 4 irons. So to correct for that, we need to change this into a 4. So now we have 4 irons, 6 oxygens, 6 oxygens. So both of these balance out now. So if you'd like to see this with the fraction method, we said we had 2 for the iron, so then we had 2 and 2. And at this point we were looking at the oxygens and said, well, we had 3 here and 2 here. So some number x, we'll call it 2 times x, because 2 is our subscript here, so 2 times x has to give us 3, because that's our number of oxygens on the right side. So this would give us x equals 3 halves. So we would put a 3 halves here. And then basically it's better practice once you have a fraction to get whole numbers out of this, so we could then put basically multiply the whole equation by 2 to get rid of this fraction. So this would give us a 4 for our final coefficient on the iron, a 3 for our final coefficient on this oxygen, and then a 2 for our final coefficient on this iron. So it ends up being the same either way, whether you do the fraction method or the multiple method, just basically whichever one comes easier to you. So another equation here, we've got copper oxide plus carbon making copper and carbon dioxide. So if we start with the coppers here, we got 2 and 1, so to correct for that, we're going to put 2 here, and now we have 2 coppers and 2 coppers, so we're good there. We can look at the carbons next. We have 1 carbon and 1 carbon, so those are good. And then here we have 2 oxygens and 1 oxygen. So what we need to do to fix this is increase the lower amount, which is this 1, so we can put a 2 here. Now we have 2 oxygens and 2 oxygens, but by putting this 2 here, it also again gets distributed, so it's going to this copper and this oxygen, so now we have 2 times 2 making 4 coppers. So 4 coppers here, we have 2 here, so we're going to need to change this into a 4 as our final coefficient. So now we have 4 coppers, we have 1 carbon, and we have 2 oxygens, so these are all balanced. So last example here, this is kind of a new concept that we haven't done yet. Basically, you might recognize these as polyatomics. This is nitrate, this is sulfate. These are polyatomics that you'd find in table E of your reference table. So when we're balancing with polyatomics, as long as we see them on both sides of the equation, so we have sulfate which matches up with sulfate here, and nitrate which matches up with nitrate. So as long as we see the same polyatomic on both sides of the equation, what we can do is treat it as one group. So we can count this, instead of distributing this 2 here, which we would get 6 oxygens and 2 nitrogens, what we can do instead is count this as one group. This would be just 2 NO3s. And then this would be 3 SO4s. And this would be 1 SO4. And this would be 3 NO3s. So instead of treating them as separate elements, we can treat the polyatomics as one group, as long as we see them on both sides of the equation, as we just showed. So if we're going to balance this now, we can say, well, we have 2 nitrates here and 3 here. So this one will be pretty easy to do using the multiple method. We could say, okay, a 2 here and a 3 here would give us the common multiple of 6, because 3 times 2 would give us 6 now for the nitrates, and 2 times 3 would give us 6 now for the nitrates on the product side. So then we could look at the sulfates and say, okay, we have 3 here and 1 here, so to correct for that, we'll put a 3 down here, and now we have 3 sulfates on the right side. So 3 sulfates, we're good with those. 6 nitrates, we're good with those. We can move on to the elements, the cations here. We have 3 barium and 3 barium, so those are good. And then we have 2 irons and 2 irons, so those are good. So you can maybe go back and try this if you want, using the elements individually and distributing these subscripts. But if you do that, you'll see that really grouping them together as one unit is the easiest way to balance these types of equations. But again, they need to appear on both sides of the equation in order for you to do that. Because if we have, let's say, a nitrate to begin with, and then we end up with some compound where it's not nitrate anymore, it's N2O4 or something like that, you can't balance it as a group because it doesn't appear on both sides. We can't try and balance these with these because they're not the same. So this is where we would have to break up into individual elements. But we'll take a look at that a little more in a future video on balancing. I hope that these examples were helpful. If you need some more help with balancing, try and go back to the beginning and work these examples by yourself. But we'll be putting another video up shortly with some more balancing examples. Thank you.